As we continue the discussion on semiconductors, the next step is extrinsic semiconductors. We already know that by doping impurities into intrinsic semiconductors, we can produce extrinsic semiconductors. I have taken up a drawing here to show the two methods of formation of extrinsic semiconductors. First, group 3 elements, doping group 3 elements and doping group 5 elements as the second method. First we will talk about doping group 3 elements. Group 3 elements, all of these group 3 elements have 3 electrons at the outermost energy level. First we take boron and show the outermost energy level only 3 electrons are present. By adding boron into this structure, I replace this silicon atom with a boron atom. What will happen? 3 electrons at the outermost energy level. I have placed 4 electrons by now. I have to remove 1. So, this place becomes a hole, a place where no electron is present. So, any electron can take up this position, this hole. Any electron can come to this one. Imagine if an electromotive force is sent from this side. Electrons, those enter this structure, can jump into this hole, and if there's another hole over here, another hole over there, those electrons can jump from one hole to another. It seems as the holes are moving when the electrons are moving. It looks like holes are moving, but what actually happens is only the electrons flow. But in science, we consider holes move under several circumstances. Then, flowing of electrons, what is it? It is an electric current once again. This method establishes the conductivity. It can improve the conductivity of the intrinsic semiconductors. Now it is mixed with boron atom, mixed with boron atoms. Those are impurities. It is an impurity, whatever it is mixed. So it is known as an extrinsic semiconductor. Then we go to the group 5, doping group 5 elements to the intrinsic semiconductors to form extrinsic semiconductors. Group 5 elements have 5 electrons, phosphorus, 5 electrons at the outermost energy level. Then I replace this silicon with a phosphorus atom. 1, 2, 3, 4, 5th electron, I can represent it like this. Extra electron or extra free electron is introduced into this structure. Electromotive force is applied from this side. The electrons, these free electrons, or not only one atom, there are many phosphorus atoms included in this extrinsic semiconductor. So there are many free electrons. When the electromotive force EMF is applied from this side, those free electrons can conduct electric current. There are free electrons present in this structure. The conductivity is somewhat stable, and we can use them in our electronic circuits. That is how the extrinsic semiconductors are produced. 2 methods. First method, the electric carriers, we conductor the holes, we consider the holes conduct electric current here. So we call them positive type or P-type semiconductors. This side, electrons conduct the electric current, so we consider them as negatively charged N-type semiconductors. In the actual condition, this is not positively charged. Holes attract electrons. That's the only reason that we call them p-type semiconductors. Don't misunderstand that they are positively charged like static electricity. They are not positively charged. They attract electrons only. That is the only property that they have to be known as p-type. P-type and n-type semiconductors. P-type extrinsic semiconductors and n-type extrinsic. Our next focus is using those p-type and n-type semiconductors, positive type and negative type semiconductors in the electronic circuits. This is the first application. You may see that two blocks are connected. Imagine that this is the p-type semiconductor and this is the n-type semiconductor. P-type and n-type. The place where they meet, the exact place where they meet is known as the p-n junction. The exact place there where the p-type and n-type semiconductors meet is known as the p-n junction. Let's see what happens as soon as the p-n junction is formed. P-type, it has extra amount of holes. I represent holes. On the p-type semiconductor, and next n-type semiconductor has extra amount of electrons there. As soon as p and n type semiconductors are kept together, these electrons jump into these holes. What happens then? Yes, of course, it is neutralization. Then it seems as these holes jump to this side because it becomes a hole there. Electrons jump over here and holes jump over there. Then they jump over there, and the area which is very closer to this p-n junction becomes neutralized. They do not contain electrons or holes in them. This area is known as the depletion region. Depletion region or depletion area. By neutralizing, electrons jump into the p-type semiconductor. Holes, you may see that holes are moving as into n-type semiconductor. Then this area becomes neutralized. This is depletion region. This area does not have free electrons or holes in it. Then the next stage, if we connect two conductor wires to these p and n type semiconductors, we become able to provide an electric current into this structure. Let's see what happens if I connect a dry cell which is 1.5 volt, positive terminal, negative terminal. Positive terminal to the p-type semiconductor, negative terminal to the n-type semiconductor. Let's see what happens next. Positive charges. We already know that holes seem to be positively charged, but they are not actually positively charged. But the positive charges of this dry cell can attract electrons towards its side. When electrons are attracted towards its side, what happens? Yes, the holes seem to be moving to this direction when electrons are attracted here. On the other hand, negatively charged terminal repels electrons. These electrons are repelled. These holes are repelled. What happens to the depletion region? When holes are repelled, then electrons are attracted to this side. When electrons are repelled from this side and holes are attracted to this side, what happens to the depletion region? The depletion region becomes very thin. The depletion region becomes very thin now. 1.5 volts. It is sufficient to break this depletion region. The holes can overcome this barrier and jump into the N-type semiconductor. Electrons can break this barrier and they can jump into the P-type semiconductor. What happens then? Flow of electrons start to flow through this PN junction. When positive terminal is connected to the P-type and the negative terminal is connected to the N-type, and if it is more than 0.7 volts, it already has 1.5 V, more than 0.7 volts can break this barrier and the electric current flows. That is what's happening in if the positive terminal is connected, positive terminal of the dry cell is connected to the P-type semiconductor and N-type semiconductor is connected with the negative terminal of the dry cell. This situation, electric current flows forward. We call this forward biasing. Forward biasing. Electric current can flow through this PN junction. That is what we call a forward biased PN junction. In our next discussion, we will talk about exchanging or interchanging these negative and positive terminals. Next, we will see what will happen if the terminals of the dry cell are interchanged. I have fixed the negative terminal of the dry cell to the P-type semiconductor, opposite as the previous one. Positive terminal to the N side or N-type semiconductor. Let's see what happens. Negative seems to be positively charged. What should happen? Yes, they are attracted. So, almost all the holes are attracted to this side. On the other hand, electrons, positive charge. Positive charge attracts these electrons to its side. It can be seen as this. All the electrons are attracted towards the terminal, all the holes are attracted towards the negative terminal. Give a name to this area. No positive or negative charge. Yes, it is once again depletion region. The depletion region broadens when it is fixed as this. Negative to the P-type, positive terminal to the N-type. The depletion region broadens means, does the electric current flow? No, there's no flow of electric current. It acts like a very hard barrier. It acts like a very hard barrier. So, this acts as a gate. No conduction of electricity when it is reverse bias. This situation is known as reverse biasing, so electric current does not flow. Controlling electric current. People do not like to use any source of energy, if they cannot control it. They are looking for this controlling. They can control the electric current by forward biasing and reverse biasing the electric current. This is the first stage that we discuss formation of electronic circuits using extrinsic semiconductors.